In the last section, we discussed how I could use information from a sample to come up with a range of reasonable estimates for a parameter of the population. We're going to kind of shift gears in this section and look at how we can utilize that sample information to make a conclusion about the population. And we're going to begin the idea of what's called hypothesis testing. In hypothesis testing, we'll have at least initially with what we're going to talk about in the next couple of sections, we're going to have an assumed value for what the population mean is equal to. We will then take a sample, look at the sample mean, and based off of that observation, determine the likelihood that the underlying assumption is true. In order to do that, we need to discuss the language of hypothesis testing. For that, we need to have what's called the null and alternative hypothesis. We need to talk about type 1 and type 2 errors, and we need to talk about how we can state a conclusion for a hypothesis test. To determine the null and alternative hypothesis, we need to define what we mean by hypothesis. A hypothesis is a statement regarding the characteristic of one or more populations. In this chapter, we'll look at hypotheses regarding a single population parameter. For example, let's suppose that previously we have done a study and we determined that 62% of American adults regularly volunteer their time for charity work. A researcher believes that this percentage is different today. Or, according to a published study in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of the call has increased since then. Or using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has increased. In all three of these examples, you'll notice that we had some given value of which we thought was the true value. And now we're proposing some alternative, that either it's different, it's greater than, or less than. The null hypothesis in a hypothesis test is that nothing has changed, so that the value that we have seen in the past is still consistent with what we should see today. So in the first example, our null hypothesis is that 62% of Americans volunteer their time. In the second example, our null hypothesis is that the average phone call time is 3.25 minutes. In the third one, our null hypothesis is the standard deviation of wine is 0.23 ounces. The alternative or research hypothesis is what we are testing. We believe that the percentage is different today. So our alternative is that the percent of people who volunteer their time is not equal to 62%, or that we believe that the length of time has increased. So we think that the mean call time is greater than 3.25 minutes. Or we think that the standard deviation has decreased. So we think that the standard deviation is less than 0.23 ounces. We do test these samples using these statements using sample data because it's impossible or impractical to gain access to the entire population. If we had all the data for the population, we would not have a need for inferential statistics. So remember, we are using sample information. Because we're basing decisions off of sample information, we can make an error in the process. Hypothesis testing is a procedure based on sample evidence and probability that we use to test whether or not statements regarding a characteristic of one or more populations is what we've proposed. The steps in the hypothesis testing are: make a statement regarding the nature of the population, collect evidence to test that statement, analyze the data to assess the plausibility of the statement, and then draw a conclusion. Okay? The null hypothesis is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference, and is assumed true until evidence indicates otherwise. So again, if we have information that we've previously thought was true, our null hypothesis is that that is still true. The alternative hypothesis, which is denoted H1, or in some books is denoted HA, or H with an alternate as a subscript, is a statement that we are trying to find evidence to support. There are three ways that we can set this up. Either we believe that whatever parameter is that we're studying is equal to some value, versus the alternative, it's not equal. That's what we saw with the first one with the population proportion. That's called a two-tailed test because it could go either direction, so either of two directions, up or down. The second is that we believe the parameter is some value versus the parameter is less than. That was what we saw in the standard deviation example. That's called a one-tailed test or a left-tailed test because we're moving to the left. Or we could have something going out to the right with a greater than symbol. So if I don't indicate a direction, it's two-tailed. If I do indicate a direction, it's one-tailed. And which direction I go indicates which tail I'm looking at. If I go less than, it's a left-tailed test. If I go greater than, it's a right-tailed test. So again, in other words, the null hypothesis is a statement of status quo or no difference and always contains a statement of equality. The null hypothesis is assumed to be true until we have evidence to the contrary. We seek evidence that supports the statement in the alternative hypothesis. Summarizing with the examples that we had, the null hypothesis for our percent of those volunteer is that the population proportion is 62%. The alternative, because we think that the average is different today, is that the proportion is not 62%. We did not indicate if we thought that proportion went up or down, so we just use a not equal. In the second one, we had a previous measurement of 3.25 minutes as an average. That's the status quo. We're going to assume that nothing has changed between 2006 and now. So our null hypothesis is that the mean cell phone call time is still 3.25 minutes. Our alternative is that the length of call has increased, so that the alternative is then that mu is greater than 3.25. And because we're moving out to the right, that is a right-tailed test. The third case, we have previously had a situation where the standard deviation was 0.23 ounces. Our null hypothesis is that nothing has changed. It's a status quo. So our null hypothesis is still that the standard deviation is 0.23 ounces. The alternative hypothesis is that that standard deviation has decreased. So our alternative is that sigma is less than 0.23. Because we've indicated a direction, it's one-tailed. Because we're moving to the left or less than, it's a left-tailed test. In this class, we will discuss how to handle hypothesis testing for the first two cases, a statement about a population proportion and statement about a population mean. We will not deal with anything with standard deviation. Those are covered in the textbook if you would like to know how to handle those. But we will only talk about the mean and the population proportion examples. Because we're using sample information to draw a conclusion about the population, we are liable to make errors. And there are two types of errors that we can get, type 1 and type 2. There are 4 different outcomes we can get from testing our hypothesis. 1, reject the null hypothesis when the alternative is true. That would be a correct decision. We do not reject the null hypothesis when the null hypothesis is true. That would be a correct decision as well. We reject the null hypothesis when the null hypothesis is true. This is an incorrect decision and it's called a type 1 error. And we can fail to reject the null hypothesis when the alternative is true. And that would also be an incorrect decision and is called a type 2 error. That's a lot of wording to try to describe what's going on. So I want to try to draw it out in table format for you. And see if we can make a little more sense of it. In order to do so, I need to pull back up my screen on my iPad here, so give me a second because it crashed. Okay, there we go. Now we're back on. So the idea is that we have the following. I'm going to have reality versus our test. Okay. In reality, we're going to have the null hypothesis is true, or the alternative is true. When we test it, we will either reject the null hypothesis, or we will fail to reject the null hypothesis. I'm not sure what language that is, but it certainly didn't look like I was writing something that could be read. There we go, hopefully. There we go. So if the null hypothesis is true and we fail to reject it, then we've made a correct decision. If the null hypothesis is false, in other words, the alternative is true, and we reject the null hypothesis, what does that mean? Well, rejecting the null hypothesis says we believe that this was a false statement. So if we reject the null hypothesis, we're saying that we think that this was not true, so that we are going to accept the alternative as being the actual case. So if the alternative is true, and we say that the alternative is true, in other words, we reject the null hypothesis, then we get a correct decision. And this is called the power of the test. The power is how often do we, or what percent of the time, do we reject the null hypothesis when it is in fact actually false. But what happens if it's actually true, if the null hypothesis is really true, and we reject the null hypothesis? Then that is an incorrect decision, and that leads to an error. And it's called a type 1 error. It's denoted by the symbol alpha. We get to set the level of alpha that we're willing to accept. So this is an error level that we will control. And I'll do a more concrete example here to help emphasize that we set this level. Now, what if the alternative is true, but we fail to reject to say that the alternative is true? So if the alternative is true, but we accept H naught or fail to reject H naught, then we've made another error, and that's a type 2 error. And it's denoted by beta. There is a relationship between type 2 error and the power of the test, in that the power is equal to 1 minus beta. The situation where H naught is true and we fail to reject being a correct decision doesn't have its own name. So we'll just leave that as correct there. Okay. So this is all still pretty abstract. Let's see if we can put this in a better context. Let's say we have a person who has been arrested for a crime. And in reality, they're not guilty. And the alternative is that in reality they are guilty. Okay. So the reality is they're either not guilty or they're guilty. One of those two is true. Now we have the results of the trial. The results of the trial will either find them guilty or we find them not guilty. Okay. If they are not guilty and we find them guilty, that is a problem. Right? If we send an innocent person to jail, we have made an error. In this case, it is a type 1 error. And that's alpha. This is a great illustration as to how we set that level. Our justice system is based off of the idea that a person is not guilty or they're innocent until proven guilty. So we go in with the assumption that they are not guilty. We set a very high threshold for finding them guilty. It doesn't have to be that they are 100% positive that this person was guilty of the crime, but it has to be beyond a reasonable doubt. The beyond a reasonable doubt means that we've set a very high threshold for convicting somebody. So we've made this chance of finding an innocent person guilty very, very small. So we've set alpha to be very small because we do not want this type of error to happen. Now, if in reality the person is guilty and we find them guilty, then the justice system has worked the way that it's supposed to. It was a correct decision, and it gave us the power of the criminal justice system. Right? We took a person who actually committed the crime, and we found them guilty. So that was the power of the test. If they were in reality not guilty and we found them not guilty, that was again a correct decision. But finding a not guilty person not guilty is again the way that it's supposed to work. But if somebody is running for district attorney, they don't talk about how often the guilty or the innocent person was found not guilty. They talk about how often the guilty person was found guilty. So they deal more into the power of the test with this comment. Now, what if the person actually committed the crime, but we found them not guilty? That means that we've let a guilty person go free, which means we have committed an error. It is different error than sending an innocent person to jail. So we're going to talk about it being the type 2 error, and we're going to set it to be beta. Note that the more difficult we make to find somebody who's innocent guilty, so the smaller we make this type 1 error, the larger we're going to make the type 2 error. The fewer innocent people we want to send to jail, the more guilty people we will let free. So note that as alpha decreases, beta increases, and vice versa. As alpha increases, beta will decrease. Right? If we're willing to overlook the fact that we're sending somebody who's not guilty to prison, then we'll end up letting less guilty people go free. Again, morally, that's not something that we're willing to accept. So again, we set alpha to be very small in this particular example. But again, the less we want to make a type 1 error, the more often we'll make a type 2 error. The more often we're comfortable making a type 1 error, the less often we'll make a type 2 error. Another example of a type 2 error is, think about a test for a disease. And we're going to run the disease, and we're going to assume that they have the disease, and they do not have the disease. And the test comes back negative, and the test comes back positive. The reason we're going to run a medical test on somebody is because we're making an assumption that they have a disease. So our null hypothesis is that they're going to have the disease. The alternative is that they do not. Rejecting the null hypothesis would be the test came back negative and said they don't have the disease. Okay. So if they have the disease and the test comes back negative, that's a type 1 error. If they do not have the disease and the test comes back negative, that's again a correct decision. If they have the disease and the test comes back positive, that's a correct decision. If, however, they do not have the disease and the test comes back positive, that's what's called a false positive, and that's a type 2 error. We typically set the threshold for what constitutes a positive test here. So we set the threshold on how often somebody who has the disease, the test will come back negative. the more stringent we make this, or the fewer people we want to, the fewer people that actually have the disease that we want to misdiagnose and say they do not have the disease, the more false positives we're going to get. This is also a good illustration of the impact of a type 2 error. The guilt-innocence one, where the type 2 error is letting a guilty person goes free, does also emphasize the impact, but this is an impact that if you're working in the medical profession or thinking about moving into the medical profession, something that plays a big role into diagnosis. Imagine having a test for cancer, and the test comes back positive. And you go in and you tell the person that they have cancer, and they actually do not have that disease. Well, depending on the type of cancer and the situation, it may be something where getting that positive result leads you to encourage them to seek treatment immediately, and they have to start taking a very invasive type of treatment. If it turns out at the end of it that they did not actually have the disease, you now have moral and ethical considerations to take into account, but you'll also have financial. Because if somebody did not have the disease and you subjected them to a horrible treatment, they're probably going to be suing you for malpractice. So what happens if we have a disease where we've done a test on it and it does come back as positive? If it's something that could be life-changing, they may run additional tests to confirm that they actually do have the disease and not getting a false positive. But this shows the dramatic effect a type 2 error could actually have on a person or on a situation. And we may look at an example like this in our example section. Okay. So if we take, for example, our percentage of Americans that volunteered and our alternative that it's different today, a type 1 error would be concluding that the population proportion was different than 0.62 when it actually is still really 0.62. So we would be rejecting a true null hypothesis. So the average has not changed, but we've said it has. A type 2 error is made if the actual percentage has changed and we conclude that it has not. So we think if in actuality it's not 62%, and we say there's no evidence to say it's not 62, then we've made a type 2 error. We've failed to reject a false null hypothesis. In the mean example, our null hypothesis was that the average length of call was 3.25 minutes. The alternative was that it was greater than. Well, if the average length of call is really still 3.25 minutes, and we conclude that the average call time has increased, we've made a type 1 error. If we reject a true null hypothesis, we've made a type 1 error. For a type 2 error, that would be the case where the call time has actually increased, but we are not able to conclude that it has increased. So we state that we still think that the mean call time is 3.25 minutes when the average is actually higher than that. So we fail to reject the mean call time is increased when in actuality it has. So we fail to reject a false null hypothesis. So alpha is the probability of rejecting the null hypothesis when it is in fact true, and beta is the probability of failing to reject the null hypothesis when the alternative is true, or equivalently when the null hypothesis is false. Again, type 1 error is something that we choose the level at which we're comfortable making that type of error. It's usually done before we collect our sample information. It's in most cases going to be 5%, and alpha is called the level of significance. Again, as we saw in our example, as type 1 error increases, type 2 error will decrease, and vice versa. So now we want to state conclusions of hypothesis test. The first thing to note is that we never accept the null hypothesis. We do not have enough information to say that that null hypothesis is true. The only way we could say that was true is if we had access to the entire population. As that will not be the case, we're using this sample information to infer something about the population. So the best that we can do is say that we fail to reject the null hypothesis. In the criminal justice system example, we don't declare the person innocent, we find them not guilty. We do not know, in many cases, that the person is innocent, but we know that there's not enough information to convict them of a crime. So we fail to reject the null hypothesis rather than accept that the null hypothesis is true. However, if we reject the null hypothesis, we're rejecting it in favor of the alternative. So we're concluding that the alternative is true. So some examples, suppose that back to our length of call time, suppose that the evidence indicates that the null hypothesis should be rejected. The conclusion we would reach then is, since the null hypothesis should be rejected, we will accept the alternative hypothesis that the mean call time has increased. So we will conclude that the average call time is greater than 3.25 minutes. We do not know what that new average call time is, we just know it's more than 3.25 minutes. Now let's suppose that the evidence indicates that the null hypothesis should not be rejected. In that case, we will say we fail to reject the null hypothesis that the mean call time is 3.25 minutes. We can't say that the mean call time is actually 3.25 minutes. We can just state that we do not have enough evidence to say it's not 3.25 minutes. So again, rejection would lead us to a statement involving the alternative. We would assume that the call time is greater than 3.25. Rejecting or failing to reject the null hypothesis says there's insufficient evidence to conclude that the mean length time is greater than 3.25 minutes. The sample evidence is consistent with a mean call length equaling 3.25 minutes. We fail to reject the null hypothesis that the mean call time is 3.25 minutes. Well, that ends our introduction to the language of hypothesis testing. We have one more section to go for this lesson, and that will begin next time.